Good morning, everybody. Hope you're all doing well. We are going to be back into presenting some new material today. We are in the lecture outline called Unit 12, Thermochemistry, and we're going to be talking about pages 6 and 7 today. And this is the first discussion of what is called the first law of thermodynamics. And you are familiar with this concept from other classes. It is an underlying theme in biology, in physics, in astronomy, in earth science. It pretty much hits every science class. And each of those classes has a slightly different little way of discussing it. Okay? So for us, the first law of thermodynamics states that energy is conserved. And you've probably heard that as you cannot create energy, you cannot destroy energy, you can only move it around, you can change it from one form of energy to another form of energy, okay? And there's a lot of different ways to talk about it. We're going to be using it to actually establish something else. Now, in an equation, we say that delta E equals Q plus W, okay? Q was heat, W was work, okay? Delta means change. So we're not talking about making energy, we're just talking about changing it. And we use this concept to introduce our favorite part of the first law, which is enthalpy. Enthalpy is the heat released in a chemical reaction at constant pressure. Now, pretty much everything that we're going to do is going to happen at constant pressure. Let's just accept that. Where are situations where pressure would not be constant? Well, going up in a spaceship, going down in a submarine, or if you are stuck in a tornado. Now, I don't think any of you are really going to be worried about chemistry in a tornado. You'll be much more concerned with physics, okay? So for what we're doing, the time frames that we're looking at, pressure's always going to stay constant. So we can almost say that enthalpy is heat. Now, enthalpy is a state function. Now, state functions are tricky little things. They are, the best way for us to talk about this, a state function is a function that does not depend upon path. Okay, it doesn't matter how you get there, it just matters that you get there. So you can do things like a delta. You can say delta E equals E2 minus E1, or delta H equals H2 minus H1. Okay, so let's picture that we have three students, A, B, and C, we'll call them, and they're down on the first floor of Bravo. Now, they all have to get up to my classroom on the 5th floor. So student A walks across the hall, finds some teacher, and, asks really politely, can you send me up in the elevator? So they get keyed in the elevator, they go up. Their altitude change was the 1st floor to the 5th floor. Okay, that's an altitude change of 5 floors. Now, how much work did they do? Not that much work. Now, student B, let's assume it's somebody from the cross-country team, just runs up the steps. They went from the 1st floor to the 5th floor. Their altitude change was 5 floors. However, the amount of work that they did was much greater than student A. Now, student C walks out of that door there on the 1st floor. Suddenly a rope comes down from their helicopter. They grab on. The helicopter winches them in. It flies up to 10,000 feet, okay? They put on a tuxedo, okay? White dinner jacket, flower in the lapel, okay? take a Walter PPK, put it in a shoulder holster. They're doing their best James Bond impersonation. So they drop back down to roof level, jump out of the side of the helicopter, grab onto that rope, swing in, crash through the window of my classroom, and land in their seat without a hair out of place. Okay, so now let's talk about their altitude change. They started at the first floor, they finished at the 5th floor. It doesn't matter that they went up to 10,000 feet. All that matters is their final position and their initial. So the change in altitude is a state function, so to speak. Okay, but the amount of work those 3 students, A, B, and C, did are all drastically different. Okay, so enthalpy is a state function. So we can do this. Now, our symbol for enthalpy is typically delta H naught. Delta change, H is what we use for enthalpy because it is essentially heat. And that's why we were using Q for heat rather than H. And this degree sign, this funny little circle, is telling us that we are at standard conditions. And what this means is 25 degrees Celsius, 1.00 atmosphere if we have gases, and 1.00 molar if we have solutions. You'll notice this is not STP. STP, put a circle in it, and draw a line through it. STP means something different. Okay? So, a little mathematical derivation, and this is one you're never going to have to do, but I do want you to see it. Delta H, or enthalpy, is defined as delta E plus P delta V. Now, we know from the first law up here at the top of the page that delta E is Q plus W plus P delta V. And we know from back on page number 2 that work equals minus P delta V. So that means we have Q minus P delta V plus P delta V. So those two are going to cancel out, and what we end up here with is that delta H equals Q. Okay? So there, enthalpy is equal to heat at constant pressure. So let's just imagine then, if we want to do these calculations based on it being a state function, that we have A turns into B and the equation's balanced. The delta H for this could be calculated by finding the delta H for B, multiplying by the coefficient from a balanced chemical equation, minus the reactants, products minus reactants. This is basically H2 minus H1. Now, we actually don't end up having to do that in this course, okay? But it's an important part of the definition itself. Okay, so that's page 6. Let's switch over. Let's go to page number 7 now. Okay, and we're going to introduce something called Hess's Law. And Hess's Law says heats of reaction are additive. Okay, now that's kind of a simple statement. What does it mean is there's a lot more to that. So when we look at this fake reaction, A turns into B. If I tell you that the enthalpy change, which is essentially just the heat involved with this reaction, is negative 10 kilojoules, I can use that to help find these others. So what about B turning into A? That's the reverse of this reaction. So if going this way it releases heat, going the other way it must absorb heat. So that would be positive 10 kilojoules. Now what if I double the reaction? 2A goes to 2B. Instead of releasing 10 kilojoules, it's going to release 20 kilojoules, twice as much. Now, reverse it and double it, it would be positive 20 kilojoules. Triple the forward reaction would be releasing triple the amount of heat, negative 30 kilojoules. Triple the reverse reaction would be absorbing 30 kilojoules. And if we had only half of the reactants, it would only release minus 5 kilojoules. So I think that's actually a pretty straightforward idea that students tend not to have a problem with. Okay. In fact, the homework that you're going to be getting tonight dealing with Hess's Law is a homework that most students end up enjoying in the long run because it's kind of a puzzle. Okay, so what if we have two reactions that are given? They're provided here. But I want to find the delta H for a reaction that's not provided. Since it only matters where I start and where I begin, I can manipulate these two equations to give me that equation and get an accurate answer. Okay, so for my reactants, I need 2NO gas and O2 gas. So I'm going to look up here to find those things. And here they are, in fact, 2NO gas plus O2 gas. So I'm just going to write that as is. I'm not going to change anything. It looks like I'm getting what I want from that reaction. And the delta H is negative 114.14 kilojoules. Now, I want N2O4 as a product, but up here in my given equations, N2O4 is a reactant. So what I'm going to end up doing is reversing that reaction. 2NO2 gas. This time will give me N2O4 gas. And instead of it being a positive, it's now a negative 57.20 kilojoules. Now, using my algebra skills, if it's on the left and it's on the right, it can cancel. And what I'm left over with is 2NO gas plus O2 gas to give me N2O4 gas. And when I add these together, I get negative 171.34 kilojoules. Okay? So that's what Hess's law looks like. Okay, the wording is kind of funny. Heats of reaction are additive, but that's what it actually looks like. And it's a pretty straightforward thing. So let's try one now that's got three equations. And the purpose of one of these equations is actually just going to be to get things to cancel. So I'm looking to have H2 and Cl2 as my reactants. I'm looking to have HCl as my product. And the first thing I just happened to notice is I have HCl here in this first equation. Okay? And it's on the wrong side. It's a reactant. I want it as a product. There's one of them. I want two of them. So what I'm going to do first is reverse the reaction. NH4Cl solid ends up giving me NH3 gas plus HCl gas, and my delta H naught is going to be a positive 176 kilojoules. But I need two of them, so I'm going to multiply this whole equation by 2, which means I also multiply that by 2. I'll let my calculator do that in a little bit. Now I need H2s and Cl2s. I'm seeing them right here. So I'm going to take that 4 H2 gas plus Cl2 gas plus, there's also an N2 gas there. I'm going to have to get rid of that somehow. Okay, and that's going to give me 2 NH4Cl solid. I haven't changed that equation, so I'm not going to change the value of delta H, negative 628.86 kilojoules. Now that is going to cancel, yay, but I got to get rid of N2s. I've got this NH3. Oh, well, hold on. This second equation, N2 plus 3H2 gives me 2 NH3s. That could make those 2 NH3s cancel. I'm going to reverse that second equation. It turns out I only need this second equation to clean things up, to help cancel some stuff here. 2 gas plus 3 H2 gas, and the delta H naught this time is a positive 92.22 kilojoules. Okay. Now, that N2 cancels that N2. Those two NH3s cancel those two NH3s. I've got 3 H2s on this side and 4 on that side. These 3 disappear, and that leaves me with just 1, which is H2 gas plus Cl2 gas gives me 2 HCl gas. And when I multiply that through and add all those numbers together, I end up getting, rounded off to a whole number, negative 184 kilojoules. I have to round off to the whole number because that's a whole number. And again, let's not turn this homework into a referendum on significant figures. If you make some sig fig boo-boos, the world is not going to end. Okay? All right, so we're going to be spending a couple of days on Hess's Law. You're going to have homeworks tonight and Friday that deal with this. And it's going to be a major part of the chapter test for this chapter. And it's going to be a big deal for those of you that are going on into AP Chem next year. All right, well, thanks for tuning in. I hope you're all having a good and healthy morning and have some fun doing this homework. Okay, this is Morgan signing off.